Good morning to all. Now, so in the previous class, okay, low sound, okay. So in the previous class, we solved some problems on the boundary layer theory, okay, and so that ends the third area, okay. Now we are entered into the fourth area, okay. So that is again, this is also from convection. This is also from convection. I already told you that only first 2 units are from conduction, the 3 units are from convection. Okay, third unit we are already completed, and then now fourth unit. This is also belongs to convection. So in this chapter we have forced convection as well as free or natural convection. I already told you that free convection is also called as natural convection. Okay. So in the forced convection, again we have, so this is the syllabus of the fourth unit. So this is the syllabus of the fourth unit. In this chapter, we have external flows and internal flows. In the forced convection, we have external flows and internal flows. So the example for external flow is the flow of the fluid, whatever it may be, over the plates, cylinders, and the spheres. Okay. So example is the air flowing over the steam pipeline. The air flowing over the steam pipeline. Okay, so that means that is example of the flow over the this one cylinders. Okay, similarly flow over the spheres. Okay, so and similarly in free convection also we have like that only plates and tubes. So if you see the external flows, so in this we have concepts about hydrodynamic and thermal boundary layer concepts. We already discussed in the previous chapter itself. So what is meant by hydrodynamic boundary layer and what is meant by thermal boundary layer. And we also there consider the flow over the plate. That means it is known as external flow. That is known as external flow. Okay. So we already studied this concept. We already studied this concept of hydrodynamic and thermal boundary layer over external flows. Okay. Now the second topic is use of empirical correlations for convective heat transfer over flat plates. So that means these are some of the external flows. These are some of the external flows. So in our syllabus we have flat plates, cylinders, spheres. Okay, so these are the external flows. External flow over the flat plate, cylinders, and spheres. So what are examples of flat plates? If we consider the blades of the turbine, or wing of the aeroplane, so we consider those as flat plates. Okay, flows over the plates, that is called external flows. So similarly cylinders and spheres. And now we have to solve some problems of this one, flat plate, cylinders, and spheres. So this is about external flows. Similarly, now we have internal flows. So that means internal flow means we know that the flow, if the flow is looking, flow of the fluid is taking place inside any object, that means through the cylinder pipeline, the steam which is flowing through the steam pipeline. Okay, the water which is flowing through the cylinder. Okay, so the gas through the spheres. So these are all the internal flows. Again, in this also we have concepts about hydrodynamic and thermal boundary layer. The main thing is division of internal flows. Division of internal flows based on the concept of hydrodynamic and thermal boundary. Now again we have some numerical problems, and these are some of the internal flows: horizontal pipe flow and annulus flow. Horizontal pipe flow and annulus flow. You know that horizontal pipe flow means the example is the steam pipeline. If you consider the or water pipeline, if that is in horizontal orientation, that is called as horizontal pipe flow. Similarly, annulus pipe flow. Annulus means you know that what is meant by annulus, concentric cylinder. If you have the concentric cylinder or concentric sphere, okay. Similarly, the plate which is having in any cross section, that is called as annulus. So this is about what we are having in forced convection. Next one is free convection. Similarly, here also we have hydrodynamic and thermal boundary layer concepts over a vertical plate. Over a vertical plate. Similarly, use of some empirical relations for vertical plates, vertical tubes, horizontal tubes, and we have some problems based upon these concepts. Okay, so this is the brief introduction about the core theory. Okay, now so we know that what is meant by convection. First of all, what is meant by convection? What is convection? Convection means if the heat is transferring takes place between the solid surface to the fluid. Okay, if the heat is transferring in between solid surface and fluid, that is simply that is called as convection. That is called as convection. We already saw in the previous unit itself, if the heat transfer is taking place between the plate and the air. Plate and the air. So plate means that is solid. Air means that is fluid. If the heat is transferring in between these two, then that is called as convection. Okay. Again, in convection we have two types, and the convection can be calculated. That means the heat transfer through convection mode can be calculated by using the formula Newton's law of cooling or heating. If we use for cooling any cooling or heating, that means that depends upon the process. If we are using for heating purpose, then we can use the that is called as Newton's law of heating. Similarly, if we use for cooling purpose, that is called as Newton's law of cooling. Okay. So we know that what is Newton's law? Q equal to HA into delta T. Delta T means surface temperature minus surrounding temperature, whatever it may be, atmospheric temperature or whatever it may be. Okay, so the difference between surface temperature and the atmospheric temperature. So by using that, we can calculate the how much amount of heat is transferred through this convection. Okay, and in convection we have two types. What are those? One is forced convection, second one is free convection. Free convection or natural convection. Free convection is also called as natural convection. Okay. So here the main concept is, if you we know that we have three types of flows: laminar flow, transient flow, and turbulent flow. Laminar flow, turbulent, transient flow, and turbulent flow. So again, those three flows based upon the Reynolds number. We know that based upon the Reynolds number, we can say that either the flow is in laminar flow or in transient flow or in turbulent flow. Okay, that means Reynolds number is very, very important in the case of forced convection. Okay, similarly, in the place of Reynolds number, we have Grashof number in the case of free convection. So we derived some equation by using Buckingham's theorem. So in that, we find that Nusselt number is function of Reynolds number and Prandtl number in the case of forced convection, and that equal to Nusselt number equal to function of Grashof number and Prandtl number in the case of free convection. That means the Grashof number plays very important role similar to the Reynolds number in the forced convection. Okay, so in this case, based upon the Reynolds number only, that means in case of forced convection, we say that according to Reynolds number only, we can classify either the flow is in laminar or in turbulent. Similarly, in the case of free convection, the product of Grashof number and Prandtl number, that is called as Rayleigh's number. Based upon the Rayleigh's number, we can say that either the flow is in laminar flow or in turbulent flow. Okay. Now we'll go to the first one. So this is the today's ILO. Okay, explain the concepts. We already discussed some of the things about hydrodynamic and thermal boundary layers of the flat plate. Okay, now we will see how to calculate this heat transfer through these concepts, and all these things we will see. Okay, so I told you that the first concept is the forced convection. The first one is forced convection. Okay, so first we study about the forced convection, and after solving some problems in this forced convection, then we go to the natural convection. Okay. So I already told you that. So this is meant by convection. Convection is the mechanism of heat transfer, okay, between a solid and the surrounding fluid. Solid and the surrounding fluid, and the fluid is in the motion. The fluid is in motion. Then only the heat transfer is taking place, and that is called as convection. Okay. It is very complex heat transfer process. It is the very complex heat transfer process. Okay, it can be expressed by using Newton's law of heating or cooling. Okay. So why we are saying that it is very complex or difficult process? Because it depends upon the fluid properties. We know that some of the fluid properties are density, viscosity. If density changes, then automatically all the parameters changes. Similarly, viscosity changes. Okay. Similarly, uh, roughness of the solid surface. Roughness of the solid surface. Suppose if we use a vertical plate or a pipe, if the roughness changes, and whenever the fluid flows over that uh, smooth surface or roughness, the surface which is having roughness, then automatically due to viscosity and these roughness, the flow depends. Again, the flow depends upon roughness and viscosity of the fluid. Okay. Similarly, shape of the material being heated. Shape of the material. Shape means is it heavy? The shape may be rectangular, square, or whatever it may be, irregular shape. Suppose if you see the aerofoil of the turbine blades, then that does not comes under any regular shape. That is called as irregular shape. That's why that is called as aerofoil shape. Okay. So shape of the material being heated or cooling and the type of the fluid flow. So we already discussed about the fluid flows, either that may be in laminar or in transient or in turbulent. So that means that's why we have to consider all these factors. We have to consider all these factors. That's why the study of convection is very complex process. That's why the study of convection, convective heat transfer is very complex method. Okay, as compared to the conduction. As compared to the conduction. Okay. So now convection can be classified as forced and natural or free convection. Natural or forced convection. Okay, depending upon how the fluid motion is initiated. We know that in the case of natural convection, we do not require any fluid motion. That means any fluid, to move the fluid, we do not require any external force. Okay, so due to the density difference only, the heat is transferring. That is called as natural convection. That means in the case of natural convection, we do not require any uh, external source, external agency. Whereas in the case of forced convection, we require some external source. So here, forced convection is a mechanism or type of transport in which fluid motion is generally generated by an external source. By an external source. Suppose if we want to cool the hot water, if we want to cool the hot water. So let us see. This is the example. So if we have water in the glass, this is the hot water. Let us say this is the hot water in the glass. We are cooling this water. If we want to cool this water, we can put in this water in the atmosphere, air. Then what happens? The heat transfer is taking place. The heat transfer is taking place. Let us say the temperature of the water is 60 degrees centigrade. Okay. So, and the atmospheric temperature is 30 degrees centigrade. Okay. The temperature of the hot water is 60 degrees centigrade and the temperature of the atmosphere is 30 degrees centigrade. So because of the temperature difference, the heat is transferred from this hot water to the atmosphere. Okay. And let us say this water temperature decreases to 40 degrees centigrade, and let us say after 5 minutes. After 5 minutes. So that means 5 minutes is taking 5 minutes is taking by the water to change the temperature from 60 to 40. So this is called as natural convection. Suppose by using the forced convection for the same parameters, we are having the water which is having at 60 degrees centigrade and atmospheric temperature is 30 degrees centigrade. We are transferring the heat. Whereas in the case of forced convection, we are using external agency. That means if you provide a fan, That means we switch on the fan. Okay, whenever the fan rotates, okay, it produces some air with higher velocity. With higher velocity, it produces some air. Okay, so because of this velocity increase in velocity. So to decrease the temperature from 60 to 40, it does not require 5 minutes. Does not take 5 minutes. Let us say that time may be 3 minutes. So that means by using forced convection, within 3 minutes, we can transfer the or we can decrease the temperature from 60 to 40. Okay. Whereas in the case of natural convection, it requires 5 minutes. Okay. So that is the difference. That is the difference between natural convection and forced convection. Okay. So that is called as external source. So for the simplicity, here we are using fan. Suppose if we want to transfer more amount of heat, then we can use blowers, compressors. Okay, and like that equipment we can use to transfer the huge amount of heat. To transfer the huge amount of heat. Okay, so forced convection is a special type of heat transfer in which fluids are forced to move. In which fluids are forced to move. So with the help of this velocity which is produced by the fan, the fluid moves with some force, okay, in order to increase the heat transfer, with a ceiling fan, pump, suction devices, blowers, compressors, or any such type of equipment we can use to transfer this uh, to create the force. Okay, so this is the difference between natural convection and forced convection. That is the difference between natural convection and forced convection. So you can explain by taking any other example. Okay, so is it clear now? Is it clear what is the difference between natural convection and forced convection? Can you say some examples? So if in a exam, if they ask you, how can you differentiate natural convection with forced convection? Or what is the difference between natural and forced convection? Then you have to explain all these things and we have to explain with by taking some examples. Okay. So is it clear or anybody is having doubt? The difference between natural convection and forced convection? Respond in the chat box. Number 8, Pawan Kumar. Number 8, Pawan Kumar. 68, Swami. Number 68, regulars. Number 68, Swami. I already told you in the previous class itself, if I ask anybody, just respond in the 2 to 3 minutes. Otherwise, I will put option. So is it clear? Anybody respond in the chat box? Number 8, okay, very good. 947. No response from 68. Swami. Okay. So this is about the difference between natural convection and forced convection. Natural convection and forced convection. Again, the main important thing is the forced convection depends upon the Reynolds number, whereas the natural convection depends upon the product of Grashof and Prandtl number, that is called as Rayleigh's number. So based upon those values of Reynolds number or Rayleigh's number, we can say that either the flow is in laminar or in turbulent. Okay, laminar or in turbulent. So I will tell you that the first thing is external flows. In our syllabus, in forced convection, we have external flows. The examples are if the fluid flows over the flat plates, cylinders, spheres. Okay. So now I already told you that in forced convection, Nusselt number is expressed as NUX equal to function of X star REX and PR. REX means local Reynolds number. I already told you that if we represent with X, that represents for local Reynolds number. If you write here L, that is called as average Reynolds number. Okay. I hope you know the difference between local Reynolds number and average Reynolds number. So suppose, what is the difference? This is very, very important. Okay. So if we have the plate, and the plate is having length L, the plate is having length L, okay, and uh, we know that so if the plate is having length L and in X direction, initially the plate is at 0 distance, and at here the distance is L. Okay, that means X varies from 0 to L. X varies from 0 to L. That means if we have the length of the plate as 5 centimeters, that means X equal to 0 to 5. 0 to 5. So suppose if you calculate the Reynolds number at any position, suppose if you calculate here after 1 centimeter, or if you want to calculate here after 3 centimeters, those Reynolds numbers are called as local Reynolds number. Those Reynolds numbers are called as local Reynolds number. Suppose if we calculate the Reynolds number at this position, that means at X equal to L, that is called as average Reynolds number. Okay, that is represented by REL. That is represented by REL. Okay, so now I told you, I explained this, what is meant by X. Subscript X has been added to emphasize our interest in conditions at a particular location on the surface. Particular location, that means, suppose if you want to calculate here, then you have to use REX. Otherwise, any point in between 0 to L, that is called as local Reynolds number. Okay, we know that where NUX is the local Nusselt number. If we use local Reynolds number, then that here we have local Nusselt number. Here use local Reynolds number, then we get only local Nusselt number. Okay. Similarly, REX is called as local Reynolds number, and here we have X star. This X star depends upon the distance, these geometric conditions. It depends upon the geometric conditions of the convection heat transfer. Okay. Now simply we can write NUA equal to function of REL and PR. So here we don't mention any X star because here we are taking the average Reynolds number. That means it does not depend upon any X star, X by L ratios and dimensionless values. Here we are calculating at the end of the plate. That's why here we have REL. We don't mention REX. So here we mention REL. That's why we do not write any X star. Okay, that is the difference between these two equations. That is the difference between these two equations. Okay, where A indicates an average distance. I already told you that this is of average values. This is for local values. This is for local values, and this is for average values. At a distance from X equal to 0 to the location of interest, where NUA is the average Nusselt number, NUA is the average Nusselt number, REL is the Reynolds number at the location of the interest. Suppose if we are calculating here, then REL. Okay, so this is very, very important. This is very, very important in these equations. These two are very, very important in forced convection. These two equations are very, very important in forced convections. Okay, and so I already told you that. Again, heat transfer depends upon, in the case of convection, it depends upon fluid properties, roughness of the surface, shape of the material, and type of fluid flow. So that means convection depends upon all these parameters. So in one case, the fluid property may change. Again, in fluid properties, we have different fluid properties, density. Similarly, if we have viscosity. Okay, so if one property changes, then automatically the calculation, the value which calculated changes. Similarly, if the roughness changes, we know that the roughness means we have. So suppose if we have a pipe like this, if we have a pipe like this, okay. So if you see with our eye, then we can say that this is the smooth pipe. Even though that is the smooth pipe, inside the pipe we have some projections. We have some roughness projections. These projections are called as roughness projections. Okay. So if the roughness increases, then automatically uh, the fluid flow changes. Why? Because the roughness acts as an obstacle. It acts as an obstacle. So it restricts the flow. It restricts the flow. That's why the flow diminishes. Okay. So this is generally, if you see with our naked eye, then we can say that this is the smooth pipe. Even though that is the smooth pipe, we have some projections. Suppose if it is the rough pipe, then automatically the projections are more as compared to the smooth pipe. So again, the flow depends upon the roughness. See the roughness. Again, shape of the material. I already told you that if we have the aerofoil shape, is like this. Okay. Okay. So this is the aerofoil shape. Then what happens if the flow is taking place over this? Okay. Because it is the irregular shape. It is very, very difficult to calculate. Similarly, type of the fluid flow. I already told you that if the flow may be laminar flow or turbulent flow. Okay. So based upon all these parameters, we are going to calculate the convection. That's why we are saying that this is the complex heat transfer method. That's why we cannot derive any expression to calculate that H value. How can you can calculate H value? We know that how we can calculate a H value. We have Nusselt number equal to H into L divided by K. You know that this is the Nusselt number. Nusselt number equal to H into L by K. Okay. If we calculate Nusselt number, if you know the Nusselt number, by using this expression, we know the length of the object, thermal conductivity of that material. Then by using this, you can calculate H value. So from this H value, after calculating that H value, we have to calculate the this H into A into Ts minus Ta. By using this expression, after calculating H, by using this formula, and then we have to use this expression, that is Q equal H into delta T. What is this one? This is the Newton's law. Of heating or cooling. Okay. So by using this expression, we have to calculate. That means to calculate heat transfer value in convection, first we have to calculate H value. Again, to calculate H, we have to use Nusselt number. This is the common procedure to calculate H value. Okay, whatever it may be, a forced convection or free convection, we have to calculate Nusselt number. From that Nusselt number, you have to calculate H value. Then you have to use this expression. Okay. Again, to calculate this H, it depends upon all these parameters. That's why it is very, very difficult method. Okay, that means this mode is very, very difficult to calculate Q. That's why we are using direct relations. And those relations are called as correlations. Those relations are called as empirical relations or correlations. That means we have direct relations. We can take from the data book. So in this chapter, data book is very, very important. Okay. So from the next class onwards, I will show now. From the next class onwards, you have to come with. That means you have to join with heat transfer data book. Okay. Otherwise, it is very, very difficult to solve the problem. Okay. Now, the first case. If you see the first case, flow of fluid over a flat surface at constant temperature. That means constant temperature of the plate. That means at constant temperature of the plate. That is very, very important. Why? Because after some time what happens, the temperature of the plate changes. Whenever the plate temperature changes, heat transfer also changes. Then it becomes very, very difficult. That's why this is one assumption. Okay. The example is, suppose if you use the heater, electric heater, to supply the current or power to the water. Okay, then what happens after some time, the temperature increases. So if the temperature increases, then automatically we have to consider that also. Then that becomes very, very difficult. That's why we are assuming that is at constant temperature. Okay, so if the first case, flow of fluid over a flat surface, over a flat surface at constant temperature. So this is very, very important. Okay, so for laminar flow, first of all, laminar flow. Then we can say that the flow is laminar in the case of flat plate. So here see, very, very important parameters are, first one is external flow. First one is external flow. I will write here because these are very, very important. External flow. First thing is external flow. So in external flow and in forced convection, again in forced convection, in external flow, okay. So if Reynolds number, roll number 31, regular 31. 1 minute. 1 second. Okay. The first thing is external flow. The first one is external flow, and in the external flow we have the plate. And in the plate, first we have to calculate the Reynolds number. Reynolds number. We know that what is Reynolds number? Reynolds number equal to rho Vd by mu. Rho Vd by mu. Okay. So if that value is less than 5 into 10 to the power of 5, if that value is less than 5 into 10 to the power of 5, then we can say that the flow is laminar. Then we can say that the flow is laminar. So see here, if the Reynolds number is, we have to calculate the Reynolds number. If the Reynolds number value is less than 5 into 10 to the power of 5, we can say that the flow is laminar. Okay, so I hope you understand this. For the flat plates, if the Reynolds number value is less than 5 into 10 to the power of 5, the flow is laminar. The flow is laminar. If it is greater than 5 into 10 to the power of 5, we can say that the flow is turbulent. Okay, I will show you afterwards. If laminar flow occurs, then we can calculate the Nusselt number, because to calculate the heat transfer, first we have to calculate the Nusselt number. What is Nusselt number? Nusselt number equal to HL by K, because here we are using A, average. That's why here we got HA. If it is NUX, that means local. Here HX. Okay, so this is very, very important difference. Okay, suppose if you want to calculate the average heat transfer coefficient, then we have to use this formula. So NUX equal to, we know that NU equal to HL by K, because it is A, here we have A. If it is A, here we have X, here it got X. Okay, so NUA equal to HAL by K, that equal to, this is the formula. 0.664 into REL to the power 0.5 into PR to the power 0.333. Okay. Similarly, if you want to calculate at the local, then the formula, instead of 0.664, we have 0.332. Now, what is meaning of that? What is meaning of that? Nusselt number average is equal to 2 into Nusselt number of X. Nusselt number of average equal to 2 into Nusselt number of x. Okay, Nusselt number of x. That's why 0.332 into 2, 0.664. Where HA is the average heat transfer coefficient, HA is the average heat transfer coefficient, and HX is the local heat transfer coefficient. Okay, this is for laminar flow. This is for laminar flow. So this is the case for laminar flow. Suppose what happens if the Reynolds number changes? Then laminar flow is converted into turbulent flow. So we already know this. So this is the boundary layer. Up to here we have laminar flow. This is transient flow and this is turbulent flow. This is laminar flow. This is transient flow and this is turbulent flow. Turbulent flow. Laminar flow, transient flow and turbulent flow. So the flow is flowing over the plate, over this plate. This is the plate, over this plate. Then first we have the laminar flow. After some time, it is converted into transient, and then after it converted into turbulent. So if Reynolds number equal to 5 into 10 to the power of 5 or less than 5 into 10 to the power of 5, that is called as laminar flow. So this value is called as, that means 5 into 10 to the power of 5 is also called as critical Reynolds number. Is also called as critical Reynolds number for the flat plate. Critical Reynolds number for the flat plate. Okay. Now we know that RE equal to rho v by mu. Reynolds number changes with respect to velocity. That means it is directly proportional to velocity because the remaining parameters becomes constant. So that's why Reynolds number depends upon velocity. Okay. So whenever the velocity changes or increases, then automatically what happens? The laminar flow is converted into transient flow. First, the laminar flow is converted into transient flow. Then, if the velocity further increases, then it converts to turbulent flow. Okay. So we know that how to calculate Nusselt number. Then after that you can calculate H. So from this you can calculate Q value. So this is in the case of laminar flow. This is in the case of laminar flow. Now next case. Then if the flow condition on the flat plate is partly laminar and partly turbulent. Partly laminar and partly turbulent. That means transition. That means a transition occurs. Transition occurs. Then what happens? So up to here it is it belongs to, some of the portion belongs to laminar, some of the portion belongs to turbulent. Why? Because here we have laminar flow. Because the velocity increases, that means then the flow converts to turbulent. The flow converts to turbulent. That's why we are saying that partly laminar and partly turbulent. Then how you have to calculate the Q value? Then this is the formula. So we can use these two directly. We can use these two directly. Okay. Nusselt number for laminar flow region. For laminar flow region, we can use these two directly. Okay. So how you got the relation between these two? That means I told you that HA equal to 2 into HX. So from this expression we got this relation. HA equal to 1 by L into integral of HX into dx within the limits 0 to L. So from this only we got HA equal to 2 into HX. So from this relation only, after solving this expression, we got this. Okay. Now, so for laminar region, we use these expressions. For laminar region, we use these expressions. Okay. Now, for turbulent. So for turbulent region, that means which is greater than 5 into 10 to the power of 5. Which is greater than 5 into, which is greater than 5 into 10 to the power of 5. If the Reynolds number is greater than 5 into 10 to the power of 5, then you have to use these two expressions. Then you have to use these two expressions. What are those? Nu equal Nu A, that means average Nusselt number equal to 0.037 REL to the power 0.8 into PR to the power 0.3. When you have to use this, then it is valid for greater than 5 into 10 to the power of 5 and less than 10 to the power 7. Okay. Similarly, local heat transfer coefficient equal to 0.0296 Rex to the power 0.8 into Pr to the power 0.333 with the same condition. Okay. So this is the expression we already discussed in the previous slide. This is about the turbulent region. Suppose mixed flow occurs. What is meant by mixed flow? Both laminar and turbulent. Both laminar and turbulent. Okay. Then you have to use this expression. Then you have to use this if it is in between 5 into 10 to the power of 5 into 10 to the power of 8. Okay. So these are very, very important expressions. That means when you have to use the expression. Okay. So if we have this is the value in between these two, then you have to use this equation. If it is below this one, you have to use these equations. Okay. So these are very, very important. And we know that Reynolds number equal to, what is Reynolds number? What is Reynolds number? Reynolds number equal to rho V D by mu. We know that Reynolds number equal to rho into V into D by mu. What are these? D is constant for the particular orientation. The diameter or length or whatever it may be, it is constant. We cannot change for the particular flow. Now, velocity is given. Now, these two are known as the properties. How you can measure these properties? That means the property of density and viscosity. So these two again depends upon the temperatures. We know that again all these properties similarly are Prandtl number UCP by K. What is Prandtl number? Prandtl number equal to mu into Cp by K. Again mu and Cp and K. Again also all these parameters depends upon temperature. Depends upon temperature. So that means these properties depends upon temperature. Okay. So here, if you consider the plate, the plate is having temperature, let us say that is Ts, and the air is having temperature Ta. Ts and Ta. So what is temperature here? If the air is flowing here, what is temperature here? Nearer to the plate, we have the same temperature. Over this, what happens after a layer in over the layer in y direction? Then the temperature decreases from Ts to Ta. Okay, so here we have some other temperature which is not equal to Ts and which is not equal to Ta. And similarly, if you see the temperature here, this is also not equal to Ts and this is not equal to Ta. So here also this is not equal to Ts and this is not equal to Ta. So if you draw the boundary layer, okay, so like in such a way that if you measure the temperatures, these temperatures are all not equal to Ta and Ts. But here, if you measure the temperature over the boundary layer, then it is equal to Ta. Okay, so that means over the boundary layer or above the boundary layer, we have the temperature is equal to the surrounding temperature, and nearer to the plate, which is nearly equal to surface temperature. Okay, that's why what we are doing is, so to use the temperature. Okay, so it can be calculated by using one formula that is called as, so this is very, very important. This is very, very important. Okay, equal to this T means Tf equal to Ta plus Ts by 2. What is Ta? Surrounding temperature. Ts, surface temperature or wall temperature divided by 2. So this is called as Tf. What is meant by Tf? Tf means mean film temperature. Mean film temperature, or that is also called as bulk temperature. That is also called as bulk temperature. So that means always we have to take the properties. That means these properties, we have to take all these properties at one temperature. That temperature is called as mean film temperature or bulk temperature. Similarly, or mean temperature, Tf, Tm, Tb. In some of the textbooks, it may be mentioned as TB, that means bulk temperature, TF, film temperature, or mean film temperature, TM, whatever it may be. That means all these properties we have to take at this temperature, and that temperature is called as film temperature or bulk temperature. Suppose if in the problem it is not mentioned anything, if it is not mentioned anything, then we have to consider these properties at TF. We have to consider it TF. Otherwise, suppose if in some of the problems they may ask to calculate the value at particular temperature, that may be either surrounding temperature or surface temperature. Suppose if we want to calculate the heat transfer at surface temperature, then we have to take all these properties at the surface temperature only. Then no need to calculate film temperature. Similarly, if you want to calculate it surrounding temperature, then you have to take all these properties at this temperature only. Okay. No need to use the mean temperature. Voice is breaking. Okay, now it is clear. Voice. So in chat box, some of the persons respond. Voice is breaking. Now is it okay? Voice. Respond in the chat box. Now is it my voice is okay? Okay, right. Okay. Now, so in this way, we have to take all the properties. We have to take all the properties. That is very, very important. That is very, very important. Okay. That's why the properties of the fluid should be calculated at temperature Ts plus Tf by 2. Okay, Tf means fluid temperature, not film temperature. This fluid temperature, that is Ta. Ts is the plate surface temperature and Tf is the fluid temperature. Fluid means that may be either air, liquid, okay, air, gas, water, or any such type of fluids. Okay, Ts or Tw. Tw means some of the textbook that may consider as wall temperature, that means surface temperature. Ts or Tw. Okay. So in this way, we have to take this. Okay. Now, all these formulas are available in the data book itself. No need to worry, but you know that where it is in the data book and how or when we have to use which formula we have to use when. That we have to know. Then only you can use those formulas. Okay. Now, if you see the data book, in the data book, in page number 112, the page number may changes according to the edition. Don't worry. Okay. So first thing is, first of all, we have to see the forced convection. We have to see the forced convection. And in forced convection, we have the external flow. These are very, very important steps. How to see? How to see? Okay. So what is that? First one is forced convection. Okay, which convey forced convection. First step. Next one. What is the next one? The external flow. Okay, so we have to consider that external flow. These are the steps. External flow. Now, after that, so here it is mentioned clearly that note properties are to be evaluated unless otherwise stated at film temperature. What is film temperature? Tw plus T infinity. That means atmospheric temperature or surrounding temperature. Okay, Tw wall temperature or surface temperature plus T infinity by 2. Unless otherwise stated. Suppose if anything is not mentioned, then you can use Tf. Suppose if it is mentioned calculated surface temperature or a calculated surrounding temperature, then you have to use that temperature. Otherwise, if anything is not mentioned, then you have to calculate it film temperature. You have to calculate it film temperature. Okay. Now, in film temperature, that means at film temperature. What is film temperature? Wall temperature plus atmospheric temperature by 2. At this temperature, we have to take the values. Which values you have to take? Density, viscosity, Prandtl number, thermal conductivity, specific heat, all those things we have to take. Okay. So I will show you while doing the problems. Okay. Now, flat plate. First thing is flat plate. We discussed about flat plate. So flat plate. So in that laminar flow, here it is clearly mentioned. in laminar flow, when we can say that the flow is laminar if the Reynolds number is less than 5 into 10 to the power of 5. That is also given in the data book. Don't worry about this. Okay. So Rex, if Rex is less than 5 into 10 to the power of 5, then we have to use these expressions. So first delta Hx, that means hydrodynamic boundary layer. Delta T, thermal boundary layer. The relation between these two, is expressed by here. Friction factor. If you want to calculate the local skin friction coefficient, this one. Average, this one. Okay. Re means rho Vd by mu. You know that. Re equal to rho Vd by mu. Okay. Now, so I already told you that constant wall temperature. We are assuming that at constant wall temperature, what is the formula? NUX equal to 0.332 into REX to the power 0.5 into PR to the power 0.333. So we mentioned, I already mentioned this formula here. So see here, this is the formula, same formula. NUX equal to HX by K equal to 0.332 into REX to the power 1 by 2. In place of 1 by 2, they give 0.5. Here PR to the power 1 by 3, 0.333. So this formula is available in the data book. This formula is available in the data book. Okay. So this is local. This is local. Yeah. So I already told you that if you have laminar turbulent region, So these are for the skin friction coefficients, average friction coefficients in laminar turbulent flow. So if you want to calculate Nusselt number, this one, laminar turbulent region. So, see here, PR to the power 0.333, PR to the power 0.333, PR power 0.333 into 0.037 into REL to the power 0.8 minus 871, similar to this one. That means this formula is okay. So this formula is available in the data book itself. This formula is also available in the data book itself. Okay. So in such a way, you have to take, you can take all these formula from the data book. Don't worry about these formulas, but you have to know where it is, where the formulas are available, in the data book. Okay. So these things are very, very important. So this data is available in page number 112, and according to the edition, this may change. Okay. Now I think it is clear to all up to here. So how to take the values from the data book, all those things. Okay. So is it clear, or anybody is having doubt? Respond in the chat box. Anybody is having doubt, we will see. Otherwise, I will take the attendance. Is it clear? Respond in the chat box. Respond in the chat box. Yeah. Now I will take the attendance. I will call some of the numbers. Okay. Those numbers are present in the participants list. Okay. So those only respond in the chat box. Otherwise, no need to respond. Roll number 6. Understood, but a little bit confusion of how to take values in data book. That's why I clearly show this with page number also. Okay, so that's why here I show with page number also. Okay, so if you practice, then it will become easy. Okay, so again I will show in while solving the problems. Okay, roll number 6, regular roll number 6. Using data book is very, very important. How to use the data book. So whenever you solve problems, then you know that how to use the data book. Otherwise, you don't know. Okay, by taking any textbook and by keeping the textbook, then you can. Okay. Roll number 41. Roll number 41. So If you have function, go to there. Okay, I don't give attendance to you. Don't worry. I don't give attendance. If you have any function, then you can go. No problem. No, no, I will give the PDF after the completion of the course unit. Okay. So in between this, if you want, you can take the screenshots. You can take screenshot. Otherwise, you have to write the notes. The main thing is you have to write the notes. Otherwise, you can take screenshots also. Okay. Regular number 6, 10, 11, 15, roll number 15, 18, roll number 18, 21, roll number 21, 23, 24, 25, 26, 27, 24. Okay. Roll number 26. Okay. Roll number 26. Okay. 29. Roll number 29. 29. 32. 34. 34. 40. Roll number 40. 43. 44. 43. 44. 43. 44. 46. 46. 48. 49. 50. 48. Okay. 50. Okay. 48. 50. Okay. 47. Okay. 51. Okay. 52. 53. 54. 55. 56. 51. Okay. 56. Okay. 55. Okay. 53. 55. Okay. 53. 55. Okay. 60. 59. Roll number 59. 60. 62. 63. 65. 67. Okay. 69. 69. Okay. 72. 73. 74. 75. 74. 75. Okay. 72 is also okay. 73. Okay. 71. Okay. 77. 78. 77. 78. 81. 83. 81. Okay. 83. So coming to LEs, lateral number 1, LE 1, 3, 4, 5, 6, 10, LE 1, 6, 10, 12, 13, 12, 13, 16, 17, 18, 21, 23, 25, 21, 23, 25, 27, 29, 30, 33, 35, 36, 39, 40, 42, 43, 47, regular 6, okay, and 18, 25, 18, okay, 25, okay, 29, okay, 63, okay, 74, 75, 75, 75, okay, 78, 83, okay, lateral 3, okay, 6, 12, 16, 6, 12, 16, 17, 18, 35, 36, 39, 35, 36, 39, 43, okay. So now I will read the option is, if anybody is there, respond. Regular 10, 15, 21, 23, 27, 34, 43, 44, 46, 52, 54, 59, 60, 62, 65, 77, laterals 1, 10, 13, 21, 23, 25, 27, 29, 30, 33, 40, 42, and 47. If anybody is there, respond. Otherwise, leave. You can leave.